Welcome to counting. There are many problems in discrete mathematics where we need to count the number of possible ways or arrangements that can be done. For example, if a password is of 6, 7, or 8 character long and has certain constraints like uh, it has uppercase letters or digit, password is required to include at least one digit, and then how many such passwords can be generated. Or for example, how many variable names of 4 character length can be created. All such kind of a problems, we need to do certain kind of an counting. And so how we can do it? So the first two basic rules are called as sum rule and product rule. So let's understand the sum rule. Let us consider two tasks. M is the number of ways to do task 1, N is the number of ways to do task 2. Now these two tasks are independent of each other. That is, performance of task 1 does not accomplish task 2 and vice versa. That is, they are totally independent of each other. In such situation, the number of ways that either task 1 or task 2 can be done, but not both, is m plus n. The figure below just summarizes how we do this. So let's consider an example. A student can choose a computer project from one of the three lists containing 23, 15, and 19 possible projects which are non-repetitive, means these do not contain the same projects. How many possible projects are there to choose from? So the addition of these three, that is choosing the project from one, that is task one, list one is task one, choosing from the other list and choice from the third list. So 23 plus 15 plus 19. Let's consider another example. Suppose that either a member of mathematics faculty or student who is a mathematics major is to be chosen as a representative to a university committee. So only one member has to be chosen. There are 37 mathematics faculty and 83 mathematics majors. Out of these, we have to choose one member. So we can choose it as 37 plus 83 ways. That is 120 ways. Consider the next example. In a version of computer language X, the name of a variable is 1 or 2 or 3 or 4 characters long. And a variable name must begin with a letter and must be different from 8 strings that are reserved for the programming. How many different variable names are there in this version of X? So I'm leaving algebra for you all, but let me just put it across. So total number of variable names that can be generated, let it be denoted by P, and P1 be the number of variable names of length 1, P2 of length 2, P3 of length 4, and P4 of length 4. So the first character has to be always alphabet, and that's why one character length variable names we can generate such 26 different variable names. For 2 character length, the first character will be alphabet, so it can be chosen in 26 ways, and the second character is either number or a character. So there are 26 numbers plus 10 digits, so it can be in 36 ways. Fourth character, 3 length variable names, same way, 26 into 36 into 30, and P4 26 into 36 into 30. Sum of these 4 subtracted by 8 will give us the total number of variables that can be generated, variable names that can be generated. Let's go to the next example for sum rule. How many strings of 4 decimal digits have exactly 3 digits that are 9? Okay, so string can have the non-9 as the first digit, or they can have non-9 as the second digit, or non-9 as the third digit, or the non-9 as the fourth digit. Thus, using the sum rule, what we can say, for each of those cases, there are 9 possibilities for the non-9 digit. So 9 plus 9 plus 9, so there are 36 strings. Let's go to the next rule, that is product rule. Let us consider two tasks. M is the number of ways to do task 1, N is the number of ways to do task 2. tasks are independent of each other, the product rule says that both the task 1 and task 2 can be done in m into n different ways. So there are 18 maths majors and 325 CS majors. How many ways are there to pick one math major and one CS major? So we can choose one math major from 18 people and we can choose another CS major from 325 CS majors. So number of ways available are 18 into 325, that is 5850 ways. How many functions are there from set A to set B? If you remember, function means there's a mapping from set A to set B. So there are 3 points in set A and each point has 4 options. So the first element will have 4 options. The second element will also have 4 options and third also will have 4 options. There are 4 into 4 into 4 ways to do this. That is 4 cube, that is 64. How many one-to-one functions are there? Now what is one-to-one? That is, let's say this point 1, the first point is mapped with one of the point. So the second point will have only remaining 3 points for the choice. So this is the mapping. Then for the second point, there are only 3 choices available. So for the first point, there are 4 choices available. For the second point, there are 3 choices available. Now, if the second one is mapped here, the third one has only 2 choices available. So it will be for the first point 4 choices into second one 3 choices into 2. That is equal to 24 possible choices. Okay, how many strings of 4 decimal digits do not contain the same digit twice? Now we want to choose basically a digit that another that is not the same than another. So first digit will have 10 possibilities. As the digit is not to be repeated, the second place will have 9 digits. That is 9 possible digits. The first one has to be omitted. Third has 8, fourth has 7. So 10 into 9 into 8 into 7. So that is 5040 ways to generate strings of 4 decimal digits that do not contain the same digit twice. How many strings of 4 decimal digits end with an even digit? So now we have first 3 digits can be chosen as, so first digit can be chosen in 10 possibilities here. Even the second one can also be chosen in 10 possibilities and third also in 10 possibilities. But last digit has to be even. So out of 10 digits, we have 5 even digits. So last digit can be chosen in 5 ways. So it will be 10 into 10 into 10 into 5 ways. This is the product rule. That is, if the 2 tasks are independent, then both can be done in A into B ways. Let's go to this some more complex problem. Count the number of ways to put the things together into various combinations. So this is a combination of sum and product rule. Even there was an earlier problem solved about the variable name generation. That was also combination of sum and product rule. So if a password is of 6, 7 or 8 character long, a character is uppercase letter or a digit and the password is required to include at least 1 digit. How many passwords can there be generated? So this problem can be solved as a sum rule, as number of passwords of 6 7 character length and 8 character length. So these to be added together to get total number of passwords, and each length password can be generated using a product rule. That is, let's calculate including those with no digits and then subtract the ones with. So 36 raised to I will give us the strings with all the possibilities, that is including alphabets and numeric, and then we'll subtract one position with that is having no digits. So 36 raised to minus 26 raised to 6. So addition of this for 7 and 8 respectively gives the total number of passwords. Let us go to an interesting problem. So we want to take a picture of 6 people in a wedding, and there are total 10 people including the bride and the groom. Now let's consider the first case. How many possibilities are there if the bride must be in the picture? So the bride must be in picture. Out of 6 positions, bride will occupy 1 position. Okay, in 6, but the position that the bride occupy can be anyone. It can be first place, second place, third place, fifth place, sixth place. So the bride can occupy the position in 6 ways. Now the next 5 places can be occupied by the remaining people. Now there are 9 people remaining. So the first place, if it is occupied by the bride, the second place would be occupied by one of the 9 people. Means there are 9 ways. The third by 8 people, one of the 8 people. Fourth by one of the 7 people. Similarly, 6 and 5 people. So it will be 9 people. So it will be 9 into 8 into 7 into 6 into 5. These are the ways the remaining positions can be occupied. The total number of possibilities are 6 into 15,120. That is 90,720 possibilities. Let's go to the next. How many possibilities are there if the bride and groom must both be in the picture? Now, bride and groom can take any one position of the out of the 6 positions. Let us say the bride takes first the position, then bride can take the position in 6 ways. Then there are 5 positions left. So groom can take the positions in 5 ways. If we do vice versa also, groom can take, if we start with the groom, then groom can take 6 positions. Groom can take 6 positions. And groom can take 6 positions. So first one will take it in 6 ways. Second one can take the positions in 5 ways. Change groom or bride, vice versa. Still the first 2 positions can be occupied in 30 ways. So first 2 positions in 30 ways. Now there are 8 people remaining out of 10. So this position can be occupied in 8 ways. This in 7, 6 and 5. So if we do the total multiplication, we have 50,400 possibilities. Okay, so how many possibilities are there if only one of the bride and groom are in the picture? If only one. There is some rule and for placing the bride or a groom, and then the product rule to find the number of possibilities when only bride is placed. Okay, so we have found this already. So there are 40,320. Now why 40,320? Though there are 6 positions, we are not going to, out of 10 people, if the first position is occupied by the bride in 6 ways, the remaining position has to be occupied by other remaining people. So that is 9 people. But 9 people will include, one of them will be groom. So that has to be excluded. So there are only 8 people left. So second position can be occupied in 8 different ways. Third in 7, 6, 5 and 4. So we have to leave groom always out. In the second case here, we have to leave bride always out. And so the total number of possibilities will still remain same. That is, and adding these two will give us the total number of possibilities that there is guaranteed that only bride or only groom is the part of the picture. So how many possibilities are there if and only one of the bride and groom are in the picture? So there are various different ways we can get it. So we have got that total ways to place the bride with or without groom is 90,720. Total ways for both bride and groom is 50,400. Total ways to place only the bride is 40,320. And then same way, repeat the same thing with the groom. And so we get still the same number. Okay, let's go to the next interesting problem. That is how many IPv4, Internet Protocol version 4. Now IP address is the identity of a machine on a network, and it's a 32-bit long. It has 2 parts. One is called as network ID and another is called as host ID. So whenever a computer has an IP address, the IP address is divided as class A, class B, class C based on the bits. How many bits are for net ID? How many are for host ID? So 7 bits for net ID is class A, 14 for bit for net ID is class B, and 21 bits for net ID is the class C. Okay, is class C. Net IDs all ones are not allowed. Host IDs that are all zeros or all ones are not allowed. Count the number of IP addresses. So this is a scenario. So class A, class B, and class C. How many valid IP addresses are there? Count the valid IP addresses for class A. We have 2 raised to 7 possibilities minus 1. So there are 127 network IPs, and 2 raised to 24 minus 2. 2 raised to 24 minus 2 are the valid host IDs. Okay, valid host IDs. So by product rule, what we can say that total number of IP addresses will be number of valid net IDs into number of valid host. So we get, so if we multiply 127 into 16, we'll get the number of valid IP addresses for class A. Similarly, we have to find number of valid IP addresses for class B and class C, and add A plus B plus C by some rule. Then we'll get the total number of IP. So we'll go to the next concept, that is principle of inclusion and exclusion. We have done this in the set theory also. So that is sum of A1 union A2 is equal to A1 plus A2 minus A1 intersection A2. Okay, so let's look at one of the problem. How many bit strings of length 8 start with 1 or end with 0, 0? So first we'll count the strings with 1, then we'll count the strings with 0, 0, and then we'll count the strings that are both having start with 1 and end with 0, 0. Count the strings with 1. So rest of the bits can be anything. So first bit is 1 and there are 120 strings. To count the bit strings that end with 0, 0, so last 2 bits are 0, 0, rest bits are anything. So 2 raised to 6 out of 8, 2 bits are reserved. So 64. And to count the strings that both start with 1 and 0, 0, 3 bits are reserved. So it will be 32. That is the intersection of the two. Okay, and if we apply the principle of inclusion and exclusion, we get the number of strings that satisfy the criteria, that is they start with 1 or end with 0, 0. Last problem is that we can use two tree diagrams to enumerate the possible choices. So once the tree is prepared or created, the result is the number of leaves, that is count the number of leaves. So let's look at the problem. Use a tree diagram to find the number of bit strings of length 4 with no 3 consecutive zeros. This is a tree, and you can find that the consecutive zeros is 3 consecutive zeros are either possible here, but which is not drawn, or it is possible here. It was possible here, but this is also not drawn. So if we just think of the number of leaves now, count the number of leaves, that is the total number of strings that can be generated which do not have 3 consecutive zeros. So 1, 2, 3, 4, 5, 7, 8, 9, 10, 11, 12, and 13. So there are 13 strings that can be generated with no 3 consecutive zeros among all the strings of length 4. Okay, this is the first video for counting. I'll be coming up with the next videos on the counting aspect, which will include the pigeonhole principle and permutation and combination.